session now. So our next speaker is Zhao, and she will speak about the EXPRES Stellar Signals. Take it away.
Thank you. Yeah, so I'd really like to thank the organizers for the chance to discuss the ESSP, or the EXPRES Stellar Signals Project, which is a discussion I've wanted to have for a long time with as many people as possible. So to that end, I'd really love it if people took out a fresh sheet of paper, or opened up an email to els@flatironinstitute.org, or for those who embrace chaos, just type directly into the Slack channel maybe. I thought what I'd do is I would give as brief as possible a summary of what we did as the EXPRES Stellar Signals Project. And then I would bring up some major questions that I thought I brought up along the way. And then I would pause for just uncomfortable enough period of time that people can think about it, maybe write down their personal thoughts of it. And then my dearest desires is that you'll either send me an email, post it to the Slack, find me sometime at the meeting and hand me your written notes, or if you want to do it anonymously, sneak it into my belongings at some point during the meeting. And I'll just have this great record of all the things that you guys think that would really help me in pursuing this project and furthering it. And so if you guys want to take out a piece of paper and write some sort of notes, I hope that this reflects what I hope ESSP is, which is truly this community-driven project for disentangling stellar signals. And so in this first stage, we had over 50 researchers, many of whom are in the room or online, who tested a total of 21 different methods for disentangling stellar signals on the same provided EXPRES data. And so by using the same data, right, we could get this self-consistent assessment of how the different methods are performing or the results that they give, and kind of use that to make future recommendations. So I think the first major result from the ESSP is that this collaboration even exists. The fact that people dedicated their time and their resources and their expertise to this project, and that we met regularly and produced the result, is not a trivial thing. And in fact, people aren't even contributing their time, they're also very generously contributing their data. And so, even though it's embarrassing, I think we will have to rebrand eventually from the EXPRES Stellar Signals Project to maybe the Extreme Stellar Signals Project. Other words that start with E are suggestions I'm taking, because we're now expanding beyond EXPRES. Many generous people from the NUID team, the HARPS teams, and the Espresso teams are also talking about sharing their data in a very similar way. And I think this is something we can all appreciate. For example, Suzanne and her team didn't have to spend their time or funding making this great conference for us, right? But they did, and we're all benefiting from it. And so because we're in this community that's so open and sharing, I think it's worthwhile to take some time to consider what exactly are the intellectual benefits that we can get from such a large, open type of collaboration where people are open to sharing what they've learned and their experiences and the things that they're working on. And so if you guys want to jot down some notes about really what we should be working towards, because I occasionally use the word data challenge. I don't like to, because I don't think the answer here is that we want to find one method that wins or that performs the best or is whatever, even if it is Gaussian processes. I won't say that in this room. But so I think it's like a type of exploration, like having all these different people contribute to different ways of trying to gauge different things about the metrics we're using or the methods that we're using. And so I will pause for 30 seconds. And you guys I would love to hear what you think, what is to be gained from a collaboration like this. So that's something we can work towards in the future. I'm very jet lagged, so this doesn't bother me at all.
Do you want real-time suggestions?
Well, if you want to write it down on realistic, because hopefully this will be fast, and then we can talk more in the end or at whatever events in this. Yeah. If you really like what you're saying, you can maybe mumble loudly and get people around you to nod. Yeah. Okay. So one of the things that I found really valuable about this assessment of the state of the field is you could kind of understand what the different axes of which different methods are considering. And so here's a summary of the different methods that people tested for the ESSP. And so they're ordered by the type of data they use, and then grouped by these different philosophies that they approach the question with. And so in the first group, we have methods that took time series, either RVs or RVs and activity indicators, and used different ways of tying what we see in the activity indicators to corrections that you think are needed for the RVs. And so it was different ways of linking the information we get about stellar activity from indicators to the RVs that we're measuring. In the next group, we have people that's primarily focused on using the correlation function, or the CCF, in various ways to try and disentangle true shifts from stellar activity. We have a group of line-by-line methods also that try to figure out different CCF masks to use or particular lines to focus on for various ends. And finally, we have a few methods that are using the full spectral format, so wavelength intensity as a way to mitigate it. And the different things that they produced were either some sort of metric, so a different type of activity indicator or some sort of indication of how much stellar signals are present in your data. Others found a new way of mitigation, so using this information or whatever you had to inform how much stellar signals you were seeing in your data, what do you do with that information to create an RV correction that you think is true to the planet signals that you're seeing? And lastly, we had a class of methods that really focused on separating the two instead. And so here you're trying to separate things that effects that you think are due to activity versus the things that you're doing to planets so that you can analyze them separately. Of course, there's some crosstalk over here. There's also some difference in the methods. Some, for example, focus purely on things that they could link directly to an astrophysical stellar effect versus other ones that look for variation in general. And so they would also take into account possible instrumental variations, things like that. And so there's a few different methods here, which again makes the head-to-head comparison difficult. But those were mostly the kind of like lines of thought that methods operated on. And so looking at this and the sort of methods that we're currently pursuing, one of the questions I thought was pertinent is, now that we understand what most people are thinking about, how complete is our current set of diagnostics? Is there something that we're missing or that we're not picking up on that's preventing us from fully getting to the bottom of the stellar signals question? For example, if we're focusing on asymmetries or shape changes, is that method going to suffer for stellar signals that generate true shifts or something like that? If we're focusing only on methods that are sensitive to all sorts of variation, is that going to change from instrument to instrument, things like that? And so is it just that we have these different metrics and they should all be tied with the mitigation methods or cross-correlated? Is there something that we're missing? And so I'll wait another 30 seconds for people to write down their thoughts about, is there any holes in what we're currently doing that we should explore more? Does this seem pretty good and we need to use it in different ways? Things like that.
Did the ESSP data have associated simultaneous photometric data?
It did, but it was ground-based and none of the methods actually make use of it.
So nobody used that?
Yeah, and it was largely non-simultaneous, which is another thing.
Right.
I'm realizing now that everyone can tell how long I'm pausing for, and it's not always 30 seconds, so I'm going to be better about that. Okay. And so finally to the main results of the project. So shown here are the 4 different EXPRES data sets that we distributed for the ESSP. They have HD numbers associated, but we picked them for like different flavors. So we had one very active star. We had one that was one of our least active stars. We had one star that was very densely sampled. And so while most only have 2 to 3 observations per night, Tau Ceti here had like 20 to 30 observations for some nights, so we could get the P mode sampling of the short-term effects. And we also had one where there was a possible planet that had often been confused for rotation or activity in the literature, and so we thought that would be particularly scientifically interesting. And so our first pass at looking at the results is we took the RVs that people returned as clean RVs, so the RVs that had all the stellar signals removed from them, and we simply took the RMS of those. So all the methods here are ordered by decreasing RMS. And so the order along the x-axis will change for each of the targets, but they'll always be getting lower. And then the height of the bar corresponds to the RMS they returned relative to the initial RMS, which is given by this dashed line, and the average single measurement position, which is given by the lower line. And then they're colored by the type of data that they input into their method. And so you could look at this for hours, and I certainly have when I didn't want to write my thesis introduction, but there's very few, I feel like, concrete conclusions that you can get out of this. It's interesting to note that the methods are ordered differently for each target, so there really wasn't like a consistent result. And one of the things that I want to highlight is that a few of the methods that you can see highlighted by these green regions return very similar final RMS values. And so if you think an RMS is a measure of how efficiently the method behaved, for example, you might assume that the ones that are returning a similar RMS value are behaving similarly. But instead, if you take a closer look, so I'm showing here instead, I'm showing here instead in this figure, the methods are ordered the same way for each of the targets. And you can see this because the bar graph I showed before is recreated in miniature in green. And the same methods that return similar RMS values are shaded in the same green colors. And so if they're returning the same RMS value, you might expect that they're removing the same stellar signal because all of the stellar signals in the data is consistent, right? And so we take each method and we just do a Pearson correlation coefficient between one method's RVs versus another method's RVs. So that way it's kind of corner plot-esque. And then we plot the correlation coefficient in terms of the color in the markers. And so if we expect it to be significant in that it has a correlation coefficient over 0.4, it's shown as a square. And otherwise it's colored, like the more red it is, the more correlated it is. So as expected, right, the diagonals all blends because you're comparing it to itself. But you can see that for a lot of these methods, even though they're used on the same data set and tracing the same stellar signals that are present in this data set, the answers don't agree with each other. And even in some cases, if they return a similar RMS, they also aren't explicitly tracing the same signal. And so because we're not sure that the methods are tracing the same signal, this shows that one RMS is a really poor metric of how well your method is performing. And so if you're trying to like tune parameters in your method or something like that, RMS might not be the best choice to do so. And two, it brings into question exactly what signals are being removed by these different methods. Is it truly stellar signals? Is it more instrumentation? Things like that.
Lily, did you have rules that people had to hold out the data that they're correcting, or these were the methods, and did all the methods do the same thing in terms of like fitting signals to some part, and or?
No, so there was no like structured training validation sets in the tests.
So in principle, somebody could have put in a method where they just removed the RV that's there and they would have gotten 0 RMS.
People love saying that. I get that every time I talk about this project. Nobody did do that, but yes.
Good, I think I'm gonna enter the next round.
Okay, great. You know you did enter this round, right? So we're confused about what the stellar signals are doing. We know that RMS isn't a great one. And so I think before we can continue these comparisons or have a constructive discussion, we should figure out what sort of tests such as training validation and or metrics such as periodograms like Annalise was saying that are needed so that we can robustly gauge how these methods are doing, what exactly they are doing, and what sort of things can we learn from each of the methods. And so this will be the last awkward pause of the conversation, I promise. But yes, Heather.
Well, people are thinking I'm answering that question. So your top left one has the most red in it. Do you have a reason why you think that might be?
Yeah, so the top, this one over here, is the one that was most active. And so in the case where the activity signal clearly dominates any other noise that could be in the data set, most people did pick up on most of the activity there. Yes, Suzanne?
And so I guess following on from what you just said, I wondered, I know I should know this from the paper, but I don't. To what extent and how do you take into account the formal uncertainties in the correlations that you measure? Or if at all, because, you know, what we're really interested in is not, is whether these correlations are significant given the noise in these measurements.
Yeah, I think I only kind of alluded to that in that when I was generating like what would count as like a significant correlation coefficient, I drew from a sample of random data points that was tuned to the error of the RVs. So when I draw from that random and figure out how many of them had a significance of greater than whatever, that's how we came up with the 0.4 number. But that's really the only way that we address that. And so there's no direct addressing of like how significant the activity signal is.
Yeah, or any variation.
Yeah. So these are the 3 questions that I think I would really love to get everyone's feedback on. I'd also, if anyone else has other questions that they would like to bring up or particularly pertinent points that they would like to say, that's all the slides I have. So I hope everyone caffeinated appropriately for during the break, because you're all giving the talk now.
I'll be considering quick process. We have plenty of time for discussion. Do you just want to pick the questions yourself? Yeah, and then we can keep it a bit more.
So good.
Well, I think it's kind of an obvious point, but I think the test would that I would like to see is the ability to retrieve an injected planet, because otherwise we never know if we absorb everything or if we correct the signal. So I think that would be nice. And the second thing, so it seemed to me in the paper that in fact a lot of the methods came down to extracting activity indicators and having a linear model of the RV. And I was wondering if it could be possible to see if the spaces, so you have spaces with a few dimensions where you project the RV activity, and if these spaces are the same or not, you know? So for example, you could project a space onto the other and see if you have a lot of residuals or not. And I think it would be really interesting to see if we are finding the same type of variations or if we are finding completely different spaces.
Yeah, that's a really great point. So for example, a lot of the methods made use of PCA in one way or another. And even if
Yes.
components in their own right are very hard to interpret, maybe we can at least see if they're comparable across the different methods when they're being used on the same things. Yeah.
I would say for the third question, starting by the end, and in relation to what Nathan said, I think we could systematically calculate detection limits in the sense of before we do any correction, the RVs came out of the instrument, what planets are we sensitive to? We could try to do that in injection and recovery, but I'm not sure that's the best way to approach it. And then we would do it at the end. Once we have corrected, what more planets are we sensitive to now? And so I think if this becomes, it would be nice if this becomes sort of a systematic metric to assess a method's performance that could in principle be comparable, more comparable between methods, and I think also more comparable if you don't actually know what's in the data, because then you just say, okay, I was not sensitive to Earth mass planet beforehand, and after I've corrected, I seem to be, and so I've gained that amount of sensitivity.
Yeah, I really love that suggestion because I feel like it gets more directly at the question we're all trying to answer here. Because while there are definitely people who hate it when we call stellar signals noise, right? The question we're trying to answer is how well can we detect planets? And so if you have a metric that addresses that more directly, it more obviously answers the thing that we're trying to assess here. Yeah. Lars, Hogg, and then Nathan.
Yeah, I think the injection recovery is a great idea. I just want to say a note of caution, especially if we want to inject at the spectrum level, which, for example, Michael is working directly with the Aran and spectral level, and I think a lot of people want to move towards that. Injecting is not easy, right? You have to basically remove the tellurics, you have to do all this. So if you do that and then inject and then use the same methods to get back, then you kind of artificially recover your signal. So we should be aware of that difficulty as well when we do these injection recovery tests, especially at the spectrum level if you want to do that.
Right, I couldn't agree more. And it's something Mikhail and I have talked about a lot. And I think we should also take a moment to think about if we do an injection recovery test, we're only explicitly testing whether or not you're absorbing planet signals. And we should think if there's any other holes in such a test that we would be missing. I think it's Hogg, Nathan, Suzanne, and then we'll go from there.
Okay, good. I'm going to derail because I want to go to the top issue. And I'll abuse the fact that I'm the oldest person in this room to say that when in the early days of cosmology, we released the Sloan Digital Sky Survey large-scale structure data for anybody to do whatever they want with, and we released the data at all levels, from the catalog to and all the imaging and all the spectra and down to the pixels, raw and reduced, everything. We released everything, and that turned the large-scale structure community into an open science community that built big software systems, did enormous analytic work about how do you measure very subtle signals in the large-scale structure. That led to all sorts of projects. We discovered the baryon acoustics feature we did all of which no one thought was even possible, and it looks very similar to the state of this field in the sense that we're trying to measure things that some people just don't think are even possible. And I think everyone really needs to work together. The whole cosmology community had to work together. So I think we can't solve this problem if we don't have large open collaborations. I'm so excited to hear about the HARPS and NUID public solar data sets. I think ESSP is a great public data set. These public data sets are going to build the collaborations, and ESSP is just an incredible example of that. But, well, anyway, I don't have a conclusion. I just don't think we can solve the problem without it, is my position. And I just love, many people in this room are building open source software, but that's only part of it. We also need open collaborations where people share results. We need open data that anyone can do anything with. And that transformed cosmology, and that transformation is just about to happen in this field. And I think you're at the apex of it.
I think you only think that because I'm currently standing at the front of the room. Sorry, Nathan and then Suzanne.
Yeah, just to follow up on Zhao's point, I think you're implicitly referring to the studies that you can do with schema, for example, with the detection limits.
Yes.
And I would agree with that if we knew that we had the right model. So I think you can trust the predictions of the posterior distribution if you assume that the likelihood is, and the prior also is somewhat true. But given the fact that the main problem we have is that we are trying to build this very model, I think the injection recovery is still a little bit more robust. And maybe it's not the end of the story, but I don't see how we could replace it. No. Maybe we could add something else, but I think it has to be done at some point.
Again?
I was going to make 2 points. One of them regarding which tests we should be thinking towards. And I'm a great fan of injection recovery tests. They are difficult and time consuming, but I think it's a worthwhile investment. But on that point, I think we might be in a situation where we're evolving towards a sort of de facto set of benchmark signals that we inject in our tests. And maybe we should have a reflection about whether that's the right set and whether we want, maybe we should collectively define a set of benchmark signals that we use. So that was my first point. The second one was about how complete our set of diagnostics and indicators and methods is. And I was wondering whether you have a feel, Lily, from writing the paper. So there were relatively few groups that attempted to both model activity in the spectrum, or if you like, mitigate it at the RV extraction stage and model it once the RVs were extracted. And I was trying to figure out whether those two approaches are getting at the same types of signals and whether we already know how much extra leverage we can get from combining them in a sequential way, potentially. Of course, the holy grail is to do everything directly, but we're not there yet. So I'm just trying to get a feel for whether that is how much overlap there is between what those two things do, essentially.
Yeah, can I respond to both of those points?
Yeah, of course.
I think you make a really good point about the injection recovery test. I think people say training validation, but there's so many different ways to do it that maybe people don't think through. For example, you could, of course, just randomly select out 10% of your data to use as a validation set and train your model on the other half. But you could also be more targeted with it. Like what happens if you take out 10% that are all in a month, or if you take out the 10% that are at a certain phase or rotation period of your star. And so there's different ways that you can construct the training validation set to understand how effective your model can be in different types of observing schedules or things like that. And so in addition to having standard things like, for example, I'm working with Annalise and Xavier and also Joe and Eric on getting a month of solar data out, which could be maybe a standard for like solar data tests as a benchmark. And we can inject certain numbers of signals in there, but then also suggest training and validation masks for that everyone could use. But then what should those look like and what do people want to test would be another conversation to have to consider. And then for the metrics question, I think you make a really good point. And one of the things that I wanted to emphasize with that column I had, how many animations did I have? It's worth going back. So one of the things that I wanted to emphasize here is that there are all these methods that are coming up with a metric and other ones that are using mitigations. And these only use classic methods of the indicators. And these are making the point that there were better ways to find metrics, right? And so I feel like these people could just get into a room, maybe this one, and just kind of like swap and see how different like the method results are if you swap out the type of indicator you use. And so that's why I really appreciate like opportunities like this one that are discussion based or like hack based. It's something we've talked about hosting at the CCA before to kind of continue this in a real time way. But Zoe, I saw that you had your hand up.
Oh, yes, I just wanted to make a point about the like training and validation splits. I worry that sometimes when you have relatively small data sets, that sometimes that's not enough. In the sense that the 10% that you take for your validation sometimes is not representative of the star. Sometimes especially if it's like only like 5 or 10 observations or something like that. So something that can sometimes work well in that case is doing some kind of k-fold cross-validation, meaning that you like take out 10%, you train on the remaining 90 or 80 or whatever split you end up taking, and then you put that back in and kind of keep on switching it out, so that you can kind of get the whole like representative of the star as much data as you have. And I feel like that would be like a really nice direction for people to go in, especially when we are dealing with relatively small data sets.
Yeah, that's a great point. Thanks. That also brings up another question of like what sort of data sets should we be collecting? Like, does this make an argument for like the terra hunting model or some way that the terra hunting model should be operated? Or if we like test on solar data alone and have that sort of overwhelming data, how much can we really learn about average night sampling or things like that? And so another thing in considering when like testing methods or forming tests is like, is there a statement that we can make for how surveys should be run going forward or how spectrographs should be designed, et cetera? Megan?
First, I just wanted to say that I think one of the intellectual benefits of collaboration can really be kind of together defining the problem that we're looking at, especially when it is such kind of a vague goal. You know, as Nathan's talk was showing this morning, like it's hard to define even the confidence of detecting a planet. And so I think that having this conversation is really awesome and is really helping us not just compare our solutions, but also compare like how we're framing the problem that we're trying to solve. And I guess on that note, and related to what you were just saying, I wanted to ask for general thoughts on what stars should we be targeting? Specifically, like, I think the traditional way has been to choose some RV standard stars that are very quiet and then try to reduce the RV RMS. But I know the EXPRES team has an RV standard star that has one known eccentric planet and a dynamical reason that you don't expect any more planets. Should we be targeting stars like that, or stars with multi-planet complex systems that we're going to try to back out, or stars like 51 Peg that have like at least one really well-known planet? Do you have any thoughts on this from your experiences?
I have many, but I also like, does anyone in the room have any thoughts about this? I'm happy to share the spotlight. But yeah, as you mentioned, like HV 3651 is the thing that EXPRES proposed. It's a very eccentric planet that's cleaned out a lot of its orbit. And so by fitting a planet, you can say what the RMS after this fit is and use that to get a measure of stability. And in fact, Sam Halverson yesterday showed, I think, a plot of 3651 as well, results from that. But I also like the idea of doing a range of activity levels, because if you have like a quiet star, it's never clear whether it's truly quiet or it's just quiet for a while, or there's hidden planets in there, right? And then we're just kind of shooting ourselves in the foot there. For example, Tau Ceti or Epsari were standard stars for so long, and they have multiple planets on both of them. And so you could also have like a standard star being a very active star, and it could be a question of, like we saw with the correlation plots, that with the most active star, all the methods agreed a lot more consistently. And so that could be a better way of giving your method enough information to mitigate all the stellar signals out. But yeah, I think maybe like with line lists, the standard star will change depending on your use case.
I think that's a good place to stop. But yeah, again, feel free to continue the discussion. Thank you very much.